Hello, I'm your host, Dan Klupany, Director of Regenerative Agriculture with Agrihub. And today we're going to have a look at energy efficiency from a perspective of improving energy efficiency on barns in a regenerative agriculture way. So here's a long-standing example with a commercial greenhouse by the name of the Denver Grow House, which put in place what's called a climate battery. And what they were able to prove very well is in a not terribly cold climate, but a pretty cold climate in Denver, this greenhouse is able to operate with much lower heating costs and virtually no cooling other than moving air with some small fans as is required. And so has been a very successful example of what is referred to as often as passive solar heating and cooling or climate batteries. Has a few different names. You could call it the economical approach or poor boy approach to geothermal in some ways. Essentially, the principles are quite straightforward. In times when we need heating, obviously we're providing hydronic heating close to the ground, or as you can see, there's some space heaters back here, etc. And really what we're interested in is keeping these plants, their roots in these hydronic grow systems. We want to keep these at an optimum temperature. And of course, heat rises. And as it rises, it's not serving really much purpose or for these plants and the water temperatures and so forth. But it is escaping. Now, in the wrong kind of structure, you're applying a great deal of heat up at those heights because you're literally forced to undertake a philosophy that says we will melt the snow as it arrives, in this case, on the polycarbonate, because if too much snow builds up on the roof, we'll have literally a cave in. So not great. Now on the right kinds of structure, a tension membrane building, then we have no risk of that snow cave in. The buildings have the shape and materials that just have the snow shedding, whether the building was heated or not, wouldn't matter. Anyway, so what the Denver Grow House and many that are doing climate battery approaches has is these kinds of tubes where there's an inline fan somewhere in this system, and the hot air is literally sucked below the ground and distributed through literally perforated weeping tile so that the heat, rather than just being wasted to atmosphere, is used once and then brought below the ground where it can rise again. And in some situations, this is a concrete floor, so it doesn't necessarily present itself. But in some situations, what is done instead is having literally trenches below these tables, or having soil or compostable systems in place. And so now what we can do is put the heat into these soils and organic matters, moist soils and organic matters. And of course, there are greenhouses that have been proven if you have a large enough compost system, and it takes a pretty large one, but there have been systems that have proven that they can actually heat a greenhouse throughout the winter using nothing but the heat from the compost. Now, at any time that those compost materials would drop below a particular threshold, then all the microorganisms that do all that composting work, they go dormant, and they take a while to come back. And so you can really risk not having that heat still happen. And then, of course, you can in addition to heating in this way, you can reverse the cycle and use the colder or cooler ground temperatures to assist in lowering greenhouse temperatures and keeping them in optimum temperatures that this butterleaf lettuce, for example, would like to have. So these approaches have been done for a long time. Um, this was literally passive solar heating and cooling was literally very much invented and advanced in Canada in the 70s. The Chinese really adopted it in Shandong province, and so what this Science Direct article showed is that there's lots of research that shows clearly that up to 70% savings can be achieved with the appropriate retrofit for commercial greenhouses. And natural gas costs were really low, and wood pellet costs were really low, etc. Mostly that stuff was kind of ignored. But now that we've seen quite a lot of pain, unfortunately, in the industry, it's getting serious attention at this time. So if I look at a typical building's heating load factor, it might look like this, and it would certainly look like this for a greenhouse. I got a certain amount of base load. Could be very small in an apartment building, for example. It could be just domestic hot water. But in a greenhouse, I'll have X number of hours, maybe even at night in Colorado, because it's at high altitude and cool mountain temperatures at night or what have you. I might be heating all 8,760 hours in a cold climate. In Colorado, maybe it's 7,000 hours, something like that. And then I got my peak heating load. And an example, it's not a one way fits all, but an example of a regenerative agriculture, highly energy efficient approach to this, we can take a significant amount of that peak heating energy load by applying a climate battery technique. It's probably not enough unless we have a large compost pile, as we described, to completely heat, but it can be enough if I've got enough surface area and so forth, where I'm capturing that solar energy. But another option, and a great option, is that we can we still need quite a lot of surface area, but we can have this means to what they call it concentrated solar, but essentially it's a concentrated solar boiler. We're going to create high hot water temperatures with the sun, and we're going to spend some quality time on this in this series. And when we have high temperatures, we can store that in insulated tanks, particularly below ground, and we can store that energy for a long time. Greenhouse operators have been doing this for a long time. And so now I'm getting past the intermittency of just solar panels that I either use it or lose it, in a relatively short period of time. I can use this, I can store it up for nighttime use, or I can store it up for use weeks and even months later. And then we might well want to address that entire base thermal load with something that is not intermittent whatsoever. Uh, Climate batteries, concentrated solar, they depend on the sun and not having too many cloudy days, etc. But with cogeneration approaches, we're using fuels that allow us to just be assured that whether the sun's shining or not, we've got the heating and energy that we need, at least for the base load, whatever that might be. So further to the Denver Grow House, this is an example of a climate battery under construction with the fellow that I learned this from, and has been building climate batteries since the 1970s. Really good team. They did a climate battery for the Rocky Mountain Institute back in the 70s, as an example. Anyway, what you see is we have a polycarbonate roof here, and these pipes will go up when they're completed as high as that one that you can see is quite near the ceiling. And the fans are going to suck this hot air from the ceiling level into these manifolds, and then it will be pushed through this perforated weeping tile. And in this case, this greenhouse, really quite beautiful. I should probably have included some pictures of it. He's at 7,000 feet of elevation. He says really cold days is when he runs his wood burning sauna on really cold days. But anyway, he pretty much heats in this way, and everything is growing in soils, and it's highly organic soils. He's constantly adding compost into these systems. And so Mother Nature and the biology that breaks down that compost that creates those really, really beautiful, healthy soils that retain water in a big way and so forth is also most of the heating, almost all of the heating for this particular greenhouse. At 7,000 feet of elevation, what he is growing, and you can see the young plants that he's brought in. You can see there's some banana plants, and there's guava plants and papaya and all of that. That's purely what he's grows in this greenhouse and has for decades. This is a climate battery partly constructed that we did for a customer. It's a residential application. They had a swimming pool that kind of ran to the end of its life. And so what we're putting in is we put lots of water storage, because water is just great for being part of your heating and cooling strategy, being that it's 800 times the density of air. Basically, this is the south side of the greenhouse, so it heats up this side of the greenhouse and heats up the water as part of our heating and cooling strategy. And then, of course, the perforated weeping tile, and we did this quite deep, just to fill in the existing pool the way the customer wanted. Now, those some people would look at the previous examples and say, yeah, the Denver Grow House was commercial, but not large scale. And then the next two examples are kind of residential, small scale solutions. Can you really scale up? Can you really make this meaningful? And the fact is these same techniques are used on very large commercial buildings. Now, this one is the Manitoba Hydro building, but it's one of many, many, particularly through Europe, that have been built. And so it's not far from the corner of Portage in Maine, in Winnipeg, a very cold climate. And what they've done is they're using geothermal and that's about 50% of their heating and cooling. As I've said before, it's good stuff, and we would certainly recommend it. You have to recognize geothermal tends to have a long payback as compared to many things. So the geothermal is about 50% of the heating and cooling. But what they call their solar chimney here is 50% of their heating and cooling. So here's a utility in a very cold climate that sells natural gas, mostly sells electricity. They mostly sell electricity to export outside of the province. And any electricity they use within the province is really subsidized, and they would have much better profit margins by exporting it. So the utility did a great job of showing there's alternative ways of doing these things. And so this 22-story building doesn't use natural gas. And it's been open since 2009. Quite a successful example. And you can see these are some of the very best energy efficient, green, net zero buildings that have been built in Canada in recent years. And what you can see is against the reference database, what the estimated energy use would be. And a number of these buildings have performed very well against what the models predicted. And then there's a few that, the models predicted something and they weren't correct at all, as compared to what happened with the actual energy use. But anyway, the Manitoba Hydro Place, as it's called, you can see just performed very, very well. And it's very successful. So there's Manitoba hydro building at using only 88 kilowatt hour of energy per meter squared, and that's all of its heating requirement, cooling requirement, electrical requirement, all factored in and put into kilowatt hour. Now, what we see with our arc sprung demonstration greenhouse is this has got a very high R rating, of course. I think the walls are R40 and that kind of thing. With a greenhouse, we're talking about an R1, whether it's glass or polycarbonate or membrane. And so the fact that we've been recording and showing this low energy use is really interesting. Now we're growing much more cool temperature crops that don't mind the building being as low as, say, 16, even 10 degrees Celsius, particularly at night. Whereas if I'm growing tomatoes and peppers and so forth, those plants, the nighttime temperatures and daytime temperatures have to be at least 18, 20 degrees, 22 degrees optimum for daytime growing. And so it would, of course, use more energy, just being clear and fair on that. But even though you're calling this a solar chimney and passive solar heating and cooling, if you look at it, it's a greenhouse, and it extends up the entire south side of the building, as we showed here. In this case, it's a glass and steel, expensive, lots of embodied energy system that is in place, but it has a quite rapid payback. And this is what the building looks like on the inside. This would typically be your exterior office facade or glass walls. And then you've added this essentially solar chimney slash greenhouse with glass. And originally, my understanding is Manitoba Hydro saw this just as a energy efficiency utility corridor, and they didn't have plans for activities. But what do you find with nice high ceilings and naturally lit space and so forth? What they found is what you'd always find is people gravitate to that. And so what they found is that, lunchtime yoga activities were pretty quick to adopt this open space, and having tables and chairs so you can have meetings in this space was really desired, and so forth. Now, essentially, what's happening? The sun's shining in. It's heating up this air very nicely, beyond what these offices, south offices, would maybe want. And that's why you see the blinds drawn and that kind of stuff. But up in the plenums here, they have fans that are moving the hot air through a plenum in the floor so that it's radiant floor heating. And they do that every 4 floors as it goes up the building. And so we're actually seeing some of this in Europe in particular, but even in Canada, as this link shows, where they're calling it another name because we can't have enough names for these things. So they're promoting passive radiant heating and cooling with what they call an exoskeleton, because what they're saying is, well, these old, really inefficient buildings, we have to retrofit all these. And if you're doing that with steel and glass, the embodied energy is incredible. The logistics of it, what do you do if there's a sidewalk here? Can you do this? Doing something with tension membrane buildings at 3 pounds per square foot, that will allow this kind of exoskeleton retrofit to potentially take place. Same thing if we're doing this on existing barns, etc., which makes a world of sense if we're going to get to regenerative agriculture and net zero in an economically intelligent fashion. So this is an example of a commercial building that has incorporated into their design for the UK a whole urban farm approach, and so that kind of stuff is potentially interesting and emerging. So what do these tension membrane buildings potentially incorporate to be really highly energy efficient and net zero? Well, they'll incorporate things potentially like the fact that they're tension membrane. They will have an unparalleled level of air tightness. We can show on these buildings that we're about a 2% exchange. Just happens to be a really great level of air exchange to be really, really energy efficient, but without worry of sick building syndrome and that kind of stuff. We can be translucent for natural light, or for a greenhouse, that kind of stuff. And in that case will be about an R1, but the air tightness is going to make us perform much higher than an R1 building. But what we can also do is we can be in a place where we can insulate up to, say, R50 if you like. More typically would be in the R30 arena. And literally what is happening to achieve that is we're showing a large gap here, but this beam would be this beam, and it would have a 12-inch spacing. Sometimes we have 9-inch spacing and room for insulation. And so what you have is your exterior wall and your interior wall. And you can see how the membrane fits in literally a rope chase on each side into the aluminum beam. And so this membrane will go in that rope chase on each side here, and it'll be one membrane from one end to the other end. And then it will be tensioned, and it never needs to be retensioned. So that's how that's constructed. Now, in this model, what we're saying is, well, we might end up with a desire to have a large gap between and something of like the Manitoba Hydro approach to a degree, something of a utility corridor. And we'd be doing that so that we can house concentrated solar in the system. When we have a large gap, we have a significant amount of air. And so we can potentially, air is a really great insulator. And so we can potentially avoid this insulation if we have the space. And it just gets us to a great level of energy efficiency, particularly with these concentrated solar parabolic mirrors. And then there's also a system we're going to show you and spend some time on, which shows you how we can also cool these buildings using modern materials, but techniques that have been used for cooling buildings in the South US, for example, adopted it, and many would argue it goes back about 800 years into Mesopotamia. And I'm told that it's literally how a lot of ant hills and termite hills are designed, interestingly enough. Anyway, so we really like that approach, and it's part of our greenhouse heating strategy. And so in this example, what we're showing is there's the parabolic mirror. It's much like what you've done in when you were a kid, undoubtedly, if you'll admit it, of course, where you took a magnifying glass and maybe an unsuspecting ant was at the wrong place at the wrong time, or you lit some paper on fire or whatever, and you saw that when I concentrate sunlight with a small amount of area, such as a magnifying glass, I can create a lot of heat in a hurry. And so what this parabolic mirror is doing is it's directing all of this sunlight to this pipe, black pipe, running up the middle here. And we can take this to high temperatures. We can take it up to, say, 80 degrees C if we like. In when we have the right piping and design, we can easily take that up to steam temperatures. So then we will have a return pipe, and then the hot water goes out this pipe, and it goes and keeps our fertigation water at really optimum temperatures, all heated by the sun. And then when there's hours that we really don't need that heat, we'll have the water go into a insulated storage tank and use it at nighttime temperature or a week later or what have you. So now we'll shift gears entirely to cooling, and we'll really focus on barn cooling, and these kinds of walls, particularly on dairy barns, are really a common sight to keep the cattle, which are really walking furnaces in some ways, at comfortable temperatures. When they're not at comfortable temperatures, it's very problematic in lots of ways. Production drops really fast, not that many degrees, and a coping strategy means that less milk is being produced. Anyway, on these 72-inch fans, Each fan is going to use about 2.4 kilowatt, give or take. And if we're in a really warm or warmer climate, we might be cooling, and particularly in dairy barns, as much as 7,500 hours of 8,760, whatever number that is. And we're showing currently a pretty low electricity number at 8 cents. I would say that the North American average right now is easily 14, somewhere in there. And that's not just including energy costs. It's important to note that that's including your distribution, transmission, admin, taxes, that kind of stuff. Anyway, what we see is one of those fans are something around $4,000 to purchase and install. And then if it's using 2.4 kilowatt in this many hours, a single fan is going to cost me almost $1,500 a year to operate. Now, in this barn example that we were looking at, they were going to need a wall of 60 of these fans. And so they had about a $240,000 capital cost just for the fans. And to operate them at 8 cents a kilowatt was going to be about $88,000 a year. All right, so what's the alternative? Well, this is a cooling system, as I say. It's called the arc cooling system. In this case, it's used in a greenhouse. It can be used in a barn or any building. In fact, the materials used are somewhat modern. This is yellow fiberglass frame. So we have the tension membrane above as our roof/ceiling. Then we create a space. As you can see, this is hanging, and then another plastic or membrane is going to be added here. And so what occurs is that, and we'll show you a little bit more of the mechanics of that in a moment, but the fact is this kind of passive cooling system uses only about 5% of the electricity of a swamp cooler, which relies on fans very much. Used a lot, quite a efficient way to cool things. Certainly disadvantages in a greenhouse. But anyway, in a swamp cooler, will use not a lot of electricity compared to those 72-inch fans. So that's very important. But also very important is the dramatic reduction of water use. About 50% less water use than a swamp cooler, if we're looking at it that way. So now what we have is this barn, and we showed you in our big picture intro part one. We showed you some pictures of actual barns and what they look like with this sort of thing. And we'll have lots of screens here and lots of ventilation coming in. And because of the Gothic shape of the buildings, the hot air will naturally rise. So these dampers or heat exhaust units can actually be wind driven, but it's easy for us to also install electric systems, and they might be 9,000 cubic feet per minute or CFM, or even higher is not a big problem. And so that will take care of quite a lot of our hours of cooling, just simply that. But when it's beyond temperatures that we want, then what happens in between the roof membrane and this plastic sitting on the fiberglass frame is we actually start misting in here. And so we're literally creating a moist cloud. There's no drippage whatsoever on the cattle, etc. But because we've captured it with these two layers of plastic, what we're creating is a buoyancy effect, and the cloud or cool air must drop, and so that cool air will drop. Basically, we're creating not a wind, but a breeze of cool natural air. And so what has been proven very, very well is that in a humid climate, we can cool by 6 degrees C. And in a dry climate, we can easily cool by as much as 20 degrees Celsius, using very little water and very little electricity. So really, really powerful, interesting system. This is one that was underway in Angola. It followed a multi-year PhD university study in the Caribbean, where it was well shown that we can cool a greenhouse even in the Caribbean 6-7 degrees, and take the greenhouse from being so hot that it's ungrowable. This particular greenhouse is for a very, very high-end resort. And yes, it grows tomatoes and so forth, but also grows lots of lettuces and so forth for the resort clientele. So to switch gears from that a little bit, we just wanted to highlight a system that Agrihub also has that literally takes small amounts of water, splits those water molecules and splits the hydrogen out. But this add-on to a diesel engine, what it allows us to do is aspirate the engine with an amount of hydrogen that burns 10 times faster than the diesel. And the advantage of that is that we're able to reduce fuel consumption with these systems by between 10 and 25%, at the same time as we're pretty dramatically reducing greenhouse gases and NOx and particulates and so forth. This is a system that is really quite inexpensive. It's been used and proven since 2014. And we have customers using it, as well as the vendor has a much larger customer base for this system, and just absolutely proven and rock solid to work and very rapid payback. So really interesting possibilities. So if you combine that to a base thermal requirement and incorporate what's called a cogen boiler into that mix, I can end up with a diesel generator or biodiesel generator, potentially. Natural gas and propane has typically been less cost, and so much more used for cogen. But anyway, whatever fuel source I choose, I have a reciprocating engine here rather than my transportation engine drive shaft for propulsion. It's going to turn a generator. We're going to produce electricity, and about 30% or so of, sometimes up to about 42% of the fuel value gets turned into electricity. But this is a liquid cooled engine, so rather than having a radiator, just send that to atmosphere, we're going to actually take that hot water, and then we've got a heat exchanger on the exhaust. And so with Yanmar systems that I've installed, for example, we capture so much of the heat, they're not that large of engines, that I can literally hold that exhaust pipe with my bare hand. But anyway, we're going to capture the heat off the engine jacket and exhaust. And so we're using this engine essentially as a cogen boiler because we're producing electricity, but also hot water that can be used for radiant heat, for space heating, domestic hot water. And we can actually use the heat and turn that into chilled water for refrigeration and air conditioning. So that would move it up to what they would call trigeneration. So this is literally what a Yanmar system would look like. Extraordinarily quiet. We've got our engine in here. It runs 7x24 and requires oil changes very infrequently. And so these systems would literally provide the radiant heat for in space heating. It's hot water for domestic hot water or any usage, whether it's a washer or whatever, at the same time as it's supplying the electricity required for the building. So I've debated many times with mechanical engineers that, pardon me, may or may not be familiar with these systems. So they'll say, well, I got a 98% efficient condensing boiler. And that's great if you have a building designed for that. I've seen lots of condensing boilers put in place because, well, the 98% efficiency was really sexy, but the building's not designed for that condensing boiler, and so it typically would run maybe at 80% efficiency or whatever. Lots and lots of non-condensing boilers that are designed to be 80% or 70% efficient. And as they age, it's not uncommon to see boilers operating at 60% efficiency. But anyway, we're just giving the benefit of the doubt. And we're saying, I got 200 units of fuel, 100 are going to be used in my boiler, and I truly have a 98% efficient condensing boiler. But I'm buying all my electricity from the grid. And some people say, wow, yeah, but I don't have any fuel use with solar panels and wind. Yeah, absolutely. With the solar panels, we don't have really high efficiency of conversion of sunlight. It helps make the grid more efficient when the sun is shining, of course. But even if we're using natural gas only for these applications, from a North American standpoint, typically we're going to be lucky to have 33 units of this fuel end up at the light socket. In fact, more commonly, you're going to be somewhere around 23%. So that conventional way of doing things, apples for apples, you're going to be lucky if you're at 65, 66% overall efficiency. And really good odds you're going to be below that for these reasons. Okay, with my cogen, I'll take same 200 units of natural gas as an example, and I'm going to have 60 units produced as electricity, so 30% efficient there, and then I'll have 100 units produced as heat, and so I'm going to be able to operate at about 80% efficiency. Sometimes just with heat use, we can be at about 90% efficiency, which is really great when we can do that. But on greenhouses, in places where I not only have a need for the heat, and the cogen will provide me affordable lighting, which, of course, if I'm buying off the grid, currently in North America, as compared to generating this on site and buying the natural gas and being close to the burner tip, as they say, I'm going to end up paying a lot more for my electricity if I'm going to run grow lights part of the time. But greenhouses very, very often are purchasing CO2. And you see why they do that is that for tomatoes, cucumbers, peppers, most plants, if I have 800 parts per million as opposed to say 400 parts per million, which is ambient current CO2 levels, will improve plant productivity by something around 15 to 20%. And what I am able to do with one of these systems, cogen, trigen, and now if I'm capturing the CO2, they're quadgen systems. I'm really, really operating at very high efficiencies and very, very cost effectively. So this is just a couple of pictures of an outdoor enclosure or an acoustic enclosure with the doors off. Here's a picture of the acoustic enclosure with the doors on. So what that means is we take these big noisy engines and they become very, very quiet. We can literally have a conversation beside them with no big challenges. It's almost like a bus idling beside you. This is a picture of an engine back here and attached, of course, to a generator inside of an acoustic enclosure. And this is an example of the actual cogen that we installed at Sprung Structures. We installed about 6 of these for Calgary Co-op, outdoors and just behind the stores. We only did one inside. So lots and lots of these installs. And the reason for it is the economics, which I'll run you through right now quickly. So in this example, we're going to buy 239 kilowatts from the grid at 14 cents kilowatt. So on an hourly basis, that's going to cost us $33.46. Then for the same amount of heat as our cogen produces in a highly efficient boiler, I'm going to purchase 1.87 GJs. And at that, in this scenario, I'm showing an $8 per GJ, which is pretty cheap these days, although it moves around. Summer, the prices are down, and winter, the prices are up. Anyway, that would cost $14.55. So that conventional cost per hour, 48 bucks, essentially. Now, the fuel for the CHP is more, right? And so we're going to use 2.44 GJs, and we're going to end up at a higher hourly fuel cost, almost $19. But the big advantage is the cogen is going to provide the same amount of electricity, 239 kilowatts, and the same amount of heat, but we're not paying for the electricity. And the only extra charge that we have is this maintenance charge, and we've used 2.5 cents, which is realistic, and that includes oil and all of these kinds of things. And so that's almost $6 an hour. And so instead of costing $48 an hour, we're at 25. All right. So if we project that out over a year, and you know what ends up being the case is that on the hourly basis, we have a almost 49% savings, and our total payback, if we're using the heat and running the system 7,271 hours per year, we have an annual savings of $167,000. And then there's greenhouse gas credits and that sort of stuff. So typically, what we've seen is as fast as say a 3-year payback, and sometimes depending on various circumstances, install costs being a big one. We might be a 8-year payback, something like that. It's kind of those sorts of numbers, and so as you see, our view is there's no alternative to efficiency. There's a number of important layers that you have to understand. They're really critical to getting to net zero the way we would like. Um, but there are ways to do this really intelligently that just make very good financial and economic sense. Would love to collaborate with you on it. And by all means, send me any comments or questions to the email on the screen. And thank you very much for your attention.